what I'm going to do today is I'm going to break it into two parts. I'm going to give a quick review on Chapter 7 entropy on some key things. And then if you look at the lecture notes, there's actually like 7 or 8, even maybe 9 more pages that I haven't covered. Most of that is example problems. So I would recommend that you look over the example problems for the test. I mean, some of the example problems are already, basically mimics of what I've already listed for example exam problems. But I would know the general approach to solving all the example problems from Chapter 7 lecture notes. Chapter 7, we have TS diagrams. And so the area in here is related to heat. And if you follow the same path from one state and back again, and you have no area within your cycle curve, that means there's no net heat transfer. So we can use the tedious question relation. We can use, the standard way of looking at change in entropy of my system from between state 1 and state 2 in interval form. There's a lot of different paths associated with ways to go about this. The main point is you have a TS diagram, and area within the cycle curve tells you about the net heat transfer. It can be net heat in or net heat out. And so I gave a rule of thumb associated with that, and that's kind of below. So one of the key things associated with Chapter 7 is this idea of an isentropic process. So if you don't know how to draw an isentropic process, if I tell you a process is isentropic for some step during a process is isentropic and you don't draw it correctly, you're going to have a lot of trouble. So this is really important. So isentropic, constant, no change in entropy process. So state 1 to state 2, you can see my delta S between, this is S of the system, from state 1 to state 2 doesn't change. And then isentropic, it's reversible, and of course, the net heat transferred in or out is 0 because there's no area under a line-based cycle, right? So then we had the rule of thumb if it's counterclockwise. Okay, so if I were to just do this integral, right, using the Tds relationships, and I was just to get an area, when it's counterclockwise, I would get a number, but it might be negative or positive, and likewise, if it's clockwise, I'd get a number. I'd have area, but it's not like I have to be down here for a negative number. So counterclockwise is analogous to a refrigerating system, and the net heat is out. So what should the sign of Q be if I had expressions to describe this and that? So I had functions,
Should be negative.
right? So this, I would get a negative number, which would represent, and the magnitude of that negative number would represent the area inside. It's Q out. Likewise, or counter, if I had functions to describe these paths or these processes, and I was to do an integral from 1 to 2 and then 2 back to 1, I would get a number, and that magnitude of the number would tell me the net heat in, because it's clockwise, 2 letters in, and this is analogous to an engine, I would have a positive number. So if you can't remember whether it's counterclockwise, clockwise, in or out, if you go through the mathematics right, you'll end up getting minus sign for out and a plus sign for in. Okay, so area inside tells me the net heat transfer, yes?
Those would not be isentropic, though.
These are not isentropic because you can see that going from state 1 to state 2, there's a change in entropy. So this is just an example, right, of the clockwise, counterclockwise rule of thumb. And then another key thing is the whole idea of entropy balance. And so just like we did first law, energy balance, all the energy in minus all the energy out is going to equal the change in internal energy in my system. We could do a mass conservation. All the mass entering my system minus all the mass leaving my system is going to equal the change in mass within of my system. And then we have entropy balance. All the forms of entropy in minus all the forms of entropy out, plus the entropy generated within my system, is going to equal the change in entropy in my system. So this is inside the boundary, crossing the boundary, crossing the boundary, crossing the boundary. So there's this extra term that deals with, it's not, usually it's always on the left-hand side, it's everything crossing, but there's this term here to keep the plus sign. Because we want to say that this is a positive quantity, so it's easy to. But the general approach, and Sgen for a system has to be greater than or equal to 0. So if I make my system isolated, that means that no heat, mass, right, can cross the boundary. So given no heat or mass can cross the boundary, there is no form of entropy in due to heat or mass. There's no form of entropy out due to heat or mass. And so I have the change in entropy of my system is equal to the entropy generated. And so I could rewrite this as that integral, right, of Q reversible over T, and then this has to be greater than or equal to 0 for an isolated system. It comes back right back to what you memorize for the definition of the second law for an isolated system. Okay, so we can do this, and we can do a bunch of things. Last part related to this, so I said this in words. Entropy transfer across a boundary is by two forms, heat and mass. So I can look at the entropy transfer due to heat related to this, right? Integral form. I can do it in summation form, where now I have all the heat inputs. There's a quantity associated with it, and that heat crosses the boundary at a given temperature. So I can add up all of these. And of course, if heat is in, this is a positive number. If heat is out, it's a negative number, right? And likewise for mass, I have mass entering my system. I have a control volume associated with that mass, right? Given it's a control volume of mass, I can define a temperature and pressure of it. Given that I know the temperature and pressure of it, I know all state functions of that control volume. Entropy is a state function, right? From the second law. There is an equation to state of the system called the entropy, right? So I know the entropy per unit mass of one control, and so this I could have 4 parts. I could have, let's say 3 parts of mass entropy due to mass. I could have water coming in, I could have gas coming in, and I could have steam leaving. So I'd have an entropy per unit mass of my water, I'd have an entropy per unit mass of my gas, and I'd have an entropy per unit mass of my steam leaving. So I can look at it in integral form, or I can go to the summation form. And then here's just another example of that. So entropy transfer by work, there's no such thing. Energy transfer by work, yes. Entropy transfer by work, no. So if I have this, mass coming in, there is no mass leaving. So if I want to look at the entropy transfer associated with mass, I have M1 times the entropy per unit mass of M1. This is defined by the temperature and pressure of M1. Now M1, of course, is associated with the control volume. And then I have my other component, mass 2 coming in. There's an entropy per unit mass of, right, of that quantity. Or I can look at it just as big S's. Entropy of mass total crossing my is big S1 plus big S2. And in this case, I have only heat coming in. So the entropy associated with heat entering is just Q in the magnitude of this divided by the temperature of my boundary at which it's crossing. So that's a quick review on entropy balance. So next thing I want to quickly review is the idea of Tds relationships. So we had these Tds relationship, and we had the first Tds Gibbs, or the second Tds enthalpy. Now we got the second, we derived this one using the first law and the Tds question form of entropy, and we replaced. So if I look at the first law, I have Q equals du minus the work done on the system. Well, minus work done on the system is just plus PV. And so I replace my Q with TDS, and then I rewrite it in terms of DS likewise, and I get these forms of the TDS relations, right? Second TDS, I use the enthalpy relation and how it's related to the internal energy. So the enthalpy is equal to the internal energy plus PV. So I take the first TDS, I put this in differential form, I replace the U with the H, and I end up subtracting my plus PdV, and I get minus VdP. Okay, so each one of these are useful in different circumstances, and just by inspection I can see that the first TDS is useful at constant volume processes. The second TDS is useful for constant pressure processes. You can use them either one for either or, but less variables in an equation usually means simpler to use. In a practice, if you want to calculate something in your head, less terms to do in your head. Okay, so related to that, we had different forms that we could do for the first and second TDS relationships related to the specific heat of the constant volume or constant pressure. This is the case where we could use average specific heats and the ideal gas law, and so we got expressions. So if there's something you might want to just memorize related to TDS relations, is the first expression, TDS equals delta U plus PdV, and this expression for the ideal gas. Because most likely, yeah, you should memorize. Okay, so for this one, the original form was TDS equals delta H minus VdP. So you should know that, and you should probably know this. Because most cases, even if I give you something that isn't an ideal gas, you can assume you can use this to get qualitative changes in the change in entropy. Even though it might not be exact, it's going to give you the right directionality, and it's going to give you within the right ballpark. So these expressions are always good. So even if I say it's a block of copper, right? So here I could just get rid of this part. If I say a block of copper, right? There's no pressure change inside. And then I just have the change in entropy of my block of copper is related to the heat capacity of the block of copper, the average one at constant pressure, times the change related to the natural log of the change in temperature of my block of copper. So even though this expression was derived for an ideal gas, it still works. And you know, we could do the same thing, but then you'd have some fudge number. It wouldn't be a gas constant, it would be some other constant. Yes?
So if it was S1 minus S2?
Well, if it's S1 minus, this is S2 minus S1, right?
Right.
So if I just do that, all I have to do is put a minus sign in front of this to make it S1 minus S2. And so if I put a minus sign in front of this, right, multiply both sides by a negative sign. So the minus sign in front of the natural log just equates to flipping these over, right? And the minus sign in front of this is equivalent to just flipping those over. Yeah. So the average specific heat analysis is useful. I'm not going to ask you to do anything other than just an average specific heat. But I would expect you to be able to answer qualitative questions associated with if you could not use the average specific heat. So I think the next slide kind of shows a plot. So when I say qualitative, right, when you can use average specific heats, you should kind of have some idea of what the specific heat kind of looks like. Hopefully you can remember that it goes to 0 at absolute 0. So another way you can remember that the specific heat goes to 0 at absolute 0 is because the specific heat has to do with degrees of freedom, and just as the temperature approaches absolute 0, right? The entropy does, because the entropy is also related to degrees of freedom, and so as you go to absolute 0, you only have one mode. So this is also related to natural log of the. But anyways, it doesn't approach 0. It approaches 0, but it approaches 0. But so this, and so average, all you're saying is that it's relatively linear. You can't use an average. This is of a pure substance. You can't use an average if at some point here I go through a phase transformation. Right? At say some temperature 2, I go from, this is for liquid, as soon as I go through a phase transformation, it's going to change. The heat capacity is going to decrease when it's a vapor or gas. So I can't use the average specific heat between 2 points here and here, but I can between here and here because it's all one phase. Okay, so I kind of want to pick up where we left off last lecture. We're talking about reversible work. And we introduced this idea of reversible work associated with flow. And so this small w, I can use big W, right? So I have a VdP. So if I think about taking a block, blowing on it, there's air coming in, which creates a pressure, right, a force per unit area, and it translates it, right? Or I just increase the pressure over here versus here. I have a pressure force, which translate. So this is my translation of a control volume work. And then in this case, for a closed system, which we've already been introduced to early in the course, is I have my work associated with a change in a control volume, so more like a piston, and so I have PdV. So we introduced this, and we had some idea of a reversible work associated with flow, and then I wanted to get to some relationships. So I can go through a bunch of stuff, and we can go reversible flow, V plus the change in kinetic potential. But then for a turbine, the work reversible for flow. Okay, so a turbine produces power, right? It's a work-producing device. So the work done on the turbine should be negative. Of course, the work done by the turbine is positive. So this is kind of a negative work of the flow in the turbine. This is the flow part. The flow is supposed to be turning everything and create. So for a turbine, this is always less than or equal to 0. When it's equal to 0, right, this flow part, that means I'm going to have maximum work. I'm going to be close to a maximum work output of my turbine. Okay, so I can look at work reversible flow versus work actual flow. And so it'd be nice, work reversible flow is equal to 0. Then, so you got this directionality associated with the turbine, energy producing device. But for a pump or a compressor or something that consumes energy, so a pump moves my fluid, right? A control volume of fluid. So in this case, the work reversible flow is greater than 0. And then I can get to some work actual flow is greater than work reversible flow, which is greater than 0. Kind of confusing. So we can talk about flow, but I think it's better if we go to here and we talk about work reversible versus work actual. Okay, so energy producing device, engine turbine, okay? Engine turbine, TDS diagram, clockwise, okay? So this plotted blue line, Q in, okay? Clockwise, energy producing device. We can go to the first law and we can equate the reversible work to the actual work. And so I should probably did the other one around. Well, I guess this is fine. So I know that Qn for engine is positive. So I'm going to get, so it's going to be clockwise. So I'm going to have this area here. So I'm going to have Q net is a positive quantity. So if I compare the reversible versus actual, I can look at Q reversible minus Q actual, work reversible. You know, there's a minus sign on this side, so it's subtracting it, right? So I got Q actual for a turbine, which I know I have the minus sign here just because of how I went from here to here. But I know this is a positive quantity. So I can bring this over to here. So I have work reversible equals work actual plus Q actual. Turbine, power producing device, Q actual is greater than 0. So based off of here to here, I can say that the work actual is always going to be less than the work reversible. And if I bring this over to here, if Q actual is equal to 0, then my work actual equals my work reversible. But usually I always have some net heat. It turns out to be in. So let's think about an engine, okay, how it works. So it goes through a reaction, right? Combustion reaction. Moves the piston, and then you compress it back. So that reaction produces what? Heat, right? Produces heat, changes the temperature and pressure of the gas within, moves the piston up, and then you have an exhaust stroke and all this other stuff, and then you get a compressed liquid again. So at each cycle, there's net heat that gets put in by the reaction. So you might think that a turbine or an energy producing device gets rid of heat, but no, it's actually a net heat in from the reaction. So I can do the counter, and let's think of a refrigerator. Now I have my steak, right? Or let's look at just a refrigerator in our house. So let's say for one cycle of cooling, what happens to the inside of my refrigerator?
Heat is removed.
You remove heat, right? You cool your steak. So let's say I put a steak in my refrigerator, I plug it in, I let the only compressor just go through one cycle, unplug it. My steak should theoretically be cooler than it was prior, right? So I keep it plugged in over several cycles, and there's net heat out of my steak, and there's net heat out from the refrigerator to the surroundings. And for the refrigerator, we get counterclockwise. Now, I said a lot there, but I'm just kind of giving you guys other methods of kind of thinking about this, heat in, heat out. So if you want to think of whether it, for a refrigerator, what was it? Was it net heat out or net heat in? Just think of your refrigerator heats up your house but cools the steak. So the refrigerator is net heat out. Now your engine, you put it in your house. If you put it in your living room and start it up, of course at some point it's going to heat up the house, but really the engine gets hot. And in order for you to keep the engine running without it blowing up, you have to have some radiator coolant to take out that heat that's coming in. Right? It's operating, it's getting hotter and hotter, and what happens when our engines get too hot? They break down. So you have to have some cooling type of method. Like a counter, you have a refrigerator. If you don't let it radiate heat out, at some point it's not going to be able to cool. The outside room's going to be too hot, and then it's not going to be able to radiate anywhere, and so it's just going to end up coming back to the refrigerator. Okay, so counterclockwise, refrigerator, so energy consuming, pump, refrigerator, whatnot. My actual work, this is consumed or output for energy consuming device. Right. So my refrigerator is never 100% efficient. My pump is never 100% efficient. So the energy I have to the pump consumes, or the energy I have to put in, is always going to be more than what the reversible case would be. There's always friction or something. So for An energy consuming device, you always have to put in more energy or do more work to get the product than you would in a reversible case. For energy producing device, an engine or a turbine, the work output is always going to be less than it would be in the reversible case where you had no irreversibilities or irreversible heat loss. So related to the test questions and the next chapter, you're going to have to remember these correlations, right? For energy producing and energy consuming systems. So I gave you some ways that I think about it to remember it, but you should come up with your own. So just another thing on work reversible versus work actual. So if I have a reversible cycle, I go from one state to the next and back. There's no reversible process, there's no area, there's no net heat in or heat out. However, if I take an irreversible path, right, I go to state 2, I go to state 3, I go to state 4, and then I come back. This is just kind of a block diagram way of looking at it. And then I end up getting, if I calculate this area, I end up getting a negative number. But the magnitude of that negative number relates to the area inside. So for a reversible cycle, Q reversible, it's always the integral, the cycle integral of TDS, but for a cycle reversible, it's equal to 0, illustrated by this. Of course, there really is no such thing as a purely reversible cycle in common, everyday technologies. So we always have something where the magnitude of this is what? Of the heat. In a real system, the magnitude is always what? For a cycle. So let's write this. Well, it's down below. So I can look at this part, right? The magnitude of Q actual, right, is always greater than or equal to 0. The magnitude is always greater than or equal to 0. For a refrigerator energy consuming system, it turns out that this is a negative number. For energy producing, this is a positive number. So I can look at this TS diagram and say I go from state 1 to state 2, and I take some path back like this part. So if I go like this and straight back, this represents counterclockwise. So I end up having a negative number associated with this. Say I go from this and then like this, I have 2 counterclockwise parts, so I get a negative number from that, a negative number from that. Now let's say I go from here, and then from here, and then from there. So this area gives me a negative number, negative number, positive number. I add them all up, and I get a total, and it looks like it's a total net heat out. So the average area for this true cycle is going to be net heat out. So any questions? And then I had some more on how you can go about doing this Q reversible minus Q actual. So just as a refresher, this part here came from the first law. Q equals delta U minus W. Okay? I'm talking about a cycle. These are cycle integrals. So what is delta U for a cycle? 0, right? You're right back at the same initial temperature and pressure, right? When you go through a cycle. So delta U, so I can put on here Q reversible, delta U reversible, work reversible, and I can do the same thing, Q actual equals delta U actual minus work actual. Now given I have a cycle, my delta U reversible or delta U actual is still 0, so I can subtract. So these big Q's is just my big Q reversible. This is that, or is this right here, the cycle integral of delta Q reversible. My big Q actual is this. So I subtract Q actual from Q reversible, give my delta U's are 0, and I end up getting this, and then I can look at my TS diagram, and for energy producing, energy consuming, I have different magnitudes of Q, and so I get these relationships, right? Energy consuming device, a pump, a refrigerator, work actual. The work I have to put into it is always more than what I would ideally want work reversible. In terms of heat, for an energy consuming device, a pump, a refrigerator, a compressor, heat actual is always less than, so that, remember this is heat out. Yeah, heat out. The heat out is always going to be less than what I would really ideally want. I can never cool my steak as much as I would ideally, as theoretically possible. Yes?
So big Q reversible is the same as this.
It's the cyclic integral,
Okay.
right?
What's
So
the-
right here is my differential, delta Q reversible, my differential amount of reversible heat. Right? I put this delta sign there because, you know, we can have exact and non-exact differentials, right? Conservative, non-conservative properties. And so heat is one of those, right? Where it has a unique path, it doesn't have a path dependence. Well, it does, but I mean, if you go back to calculus, you'll see the difference between D's and deltas in terms of non-conservative and conservative, and path dependence and non-path dependence. So, my differential amount of heat reversible, integrate that over a cycle, that has to equal my total heat reversible, right? Differential amount of heat actual, integrate that over a cycle, that has to equal my total heat. And likewise, the same for work. My differential amount of work, in the actual case, cyclic integral gives me my total actual amount of work. My differential amount of work reversible, integrate that over a cycle, that has to equal my total amount of reversible work for a cycle. Now I did this for cycles so we could make delta U's equal to 0. This could be much more complicated and get similar answers by just going from one state to the next, but then I would have to include my delta U's for each case. But these are the main points at the bottom. Energy output device. I never get as much output as I would ideally, theoretically, is possible. The heat out, or the heat into my system, is always going to be more than what I would want. So in a really good reversible engine, there would be no net heat in. Remember when we had that piston problem and I compressed it to increase its temperature? And then it responded back, and all of that initial heating pushed back right to where I was. So I came right back to the same temperature. There's no heat, right, out of the system or into the system. So in an engine, you always have, right, more heat in than I would like and less work out than I would like. And the counter axiom for here. So I would say that you should definitely be able to write those out.